Hi everyone! In this video I want to share with you how to build a node graph in C++ and later on in Rust. Let's begin with what node graph is. Node graph is a graph of nodes which are connected, and those connections, they come out of pins. Okay, so I'm going to draw the pins and I'm going to draw the connections. Okay, so this is a very simple node graph when we have one source node, one transformation node, and one destination node. Source node is providing source data, for example an image. Transformation node is performing some transformation of this data, and then destination node is collecting the data into some sort of storage, maybe a file, maybe a texture in a video card or somewhere, right? So how do we implement such a graph in C++? Let's start with C++. Let's start by defining what node is. So class node. All right. So we're gonna create a node class with the structure that is protected and two virtual methods which allow us to process the graph forwards and backwards. Let's look at the graph. When processing forwards, we will start from this source node and we will process in this direction. Okay? So we're gonna take the value from this source node, send it to this output pin. It will be received on this input pin on the transform. Transform will perform transformation, will send the result onto output pin, and then the destination will receive it on the input pin, and it will do something like that. Okay? And process backwards. Process backwards starts from the destination. It goes into connected nodes. So from the input pin, it goes to the connection to the output pin of the node, and it asks for data. But transform node doesn't have data on the output pin. Transform node goes into a source node. So it asks through its input pin the data from the output pin of a source node. And then output pin of a source node will execute whatever is in the source node to provide data on that pin. And what will happen? Source node will provide data on that pin. The data will travel into the input pin of the transform. The transform will perform the transformation and output the data onto its output pin, which will then get transmitted into the input pin of destination, which will then be ingested by destination. All right, so this is processing backwards. So this is my pin class. Pin class is gonna take some t for the data that we gonna transmit through that pin. Okay, it will be attached to some node. So you can see there is a get owning node. There is an mNode property of that pin, so node to which this pin is attached. And there is an opposing pin, the connection, the opposing pin, the pin that we are connected to. So if you look at the picture, if we take any of those pins, so if I, for example, take this pin, the node is this transform node, and the opposing pin is this pin here, okay? But if I take this pin, the node is this source node, and the opposing pin is this input pin here. So they're symmetrically connected, right? All right, so let's see the connection method. So you see there's a protected connect method which allows us to connect a pin into a pin. This way we set the opposing pin for this pin, and we set this to be opposing pin for the other pin, right? So this is how we make it symmetric connection. When we disconnect, which is a public method here, we just null both. So we null ourselves, the opposing pin, but before that we null opposing pin, the opposing pin, which is us as well, right? So this is how we disconnect. Once again, we support right now only the situation where we have connections like this. So pin-to-pin connections are one-to-one. There's one pin on the one side and one pin on the other side. This is our current implementation. Let's now specialize pin to be input and output pin. Let's start with the input pin. So the input pin expands pin class, okay? And it has connect method, which is public method, and allows to connect output pin. So you remember that the connect in the pin method allows to connect any pin to it, but it's protected. And it is up to the ref class, which is input pin, to decide that only output pin can be connected to the input pin. We also define the function called receive data, and the receive data will get the connected pin, okay? And it will take from the connected pin the data and will set it into current pin. So what this does for the input pin, we take in this input pin the data from this pin because it's connected, so we do and collect the data from here, and we set it here. So the data that was here gets copied over here, okay? The data goes here. All right, we have one missing component here, which is output pin. We need to declare it first. We create this forward declaration because we will define output pin afterwards. Let's define output pin. So this is our output pin. It is opposite to input pin, so the connect method allows input pin to be connected. And we can see that the implementation simply calls pin connect. So the base class pin t connect. The idea is that the base class pin connect will accept any type of a pin, so it's protected. Whereas output pin connect only accepts input pins, so you can only connect input pin to an output pin. So you can use connect on the output pin to connect input pin, or you can use connect on the input pin to connect output pin. The direction in which you're connecting is up to you. Another thing about the output pin is that now it has send data. Input pin has receive data, okay? And output pin has send data. Send data is symmetrical to receive data. So it takes the connected pin and sets the data for the connected pin to be the same as current data of current pin. So the way this works is for this pin, send data will take the opposing pin, which is this one, and it will take this data on this current pin and set it here on the input pin. Alright, we have some missing methods unimplemented. If we look backwards, we have connect method. Let's implement connect method. So input pin connect method is also simply calling pin connect, similar to output pin connect method. The difference between output pin connect method is that it takes input pin, whereas input pin connect takes an output pin. So this is a way for me to ensure that someone who's using input pin is going to always connect an output pin to it, and someone who's using output pin will always connect an input pin to it, and there won't be any mistake. Right, let's define some nodes. Source node is a class that extends a node. You can see that here it extends the node in a private fashion. It doesn't inherit publicly from the node. The destructor is public. We remember that node has been defined with protected destructor. So this derived class will be able to destruct node because protected destructor is reachable from the derived class, right? And the derived class has to implement these two methods, process forwards and backwards. Now, this is our derived class source node, which will represent some source. And in our demonstration case, the source will just have a load value function that we will use to put some value into it from our program, for our demonstration program. So load value is a helper function we will use to put some value x into the output pin of our source node. So when we call load value on our source, we're effectively putting this value on this pin here, on the output pin of the source node. We can see implementation of the process forwards and process backwards. So process backwards is an empty method. It's potentially Liskov rule violation, although it's not because it doesn't violate invariance. However, it's an empty method, right? It's empty because there is nowhere to go backwards from the source node. For source node, we define process forwards by calling send data on the output pin and propagate forwards. What that does, it will send its data from this output pin into this input pin here that's connected, okay? And then it will tell this pin to propagate in this direction forwards, meaning that this pin will go to this node and tell it to process the data and output into its output pin the result, and then this pin will copy the value into its output pin, and it will tell attach node destination to process the result. Okay, so let's implement the destination node. So this destination node is called target node. It has one input pin. The process forward is implemented as empty, which we can see that this node doesn't have any output pins, so there is nowhere to go in this direction. And it implements process backwards by telling input pin to propagate backwards and then receive the data. So destination node implements process backwards by going to its input pin and telling it to propagate backwards. The input pin will then go to its connected output pin and tell it to process backwards, which will go to this transform node and tell the transform node to process backwards, which will go to its input pin and tell to propagate backwards, which will tell connected output pin of the source node to propagate backwards, which will tell the source node to process backwards, right? So the flow goes in this direction, right? All right, let's implement the transform node. So this is our transform node. The transform node extends the node, again, in private fashion. It have a public destructor, so we can create it on stack. And it implements both process backwards and process forwards. You can see that it has input pin and output pin. In order to process backwards from transform node, we're going this way. So we need to go to input pin of the transform node and tell it to propagate backwards, right? So process backwards goes to input pin and tells it to propagate backwards. Once the input pin finishes propagation, we receive on the input pin the data, and then we use that data for our function, for our transformation function, which we have in this transform node. So we say get input pin, get data, and we set this on our output, right? So the way it goes, we go from the transform node to the input pin, tell it to propagate backwards, and then process backwards, and then there should be data here, and then from here we say receive data, which will go to the connected pin, and we'll take this data and copy it here. Okay, and then we take this data and process it here with the function, and the resulting value we will put here on the output pin. Okay. Now the process forwards. Process forwards works the other way. So process forwards assumes that the input is valid. So it takes the data from the input, puts it into a function, a transformation function, and sets the result into the output pin. After that, it sends the data from the output pin to connected pin and tells output pin to propagate forwards. So what happens is we have data here on the input pin, we read it in, we call a function with this data, we set the output pin data to be the result, then we tell the output pin to send that data, and that will copy this data to this connected pin, okay? And then we tell the output pin to propagate forwards, which will go to connected pin, and it will tell its node to process forwards, which will ingest this data. Let's build a graph now. Alright, so this is our demo function, which builds a graph. And it builds a graph exactly like on this picture here. So we'll have one source node, one destination node, and one transform node, and they are connected in exactly this way. Let's look at the code. So we have a transform node that has some function in it, So we have this function here. This is some lambda. So I use decal type funds to decide what the type of this is. And then I use this transform node and connect its input to the source node output. So we have this source node, we have this target node, and I'm connecting source node output to transform node input pin. Okay, and I'm connecting transform node output to target node input pin. Okay, so this is the connection. And next, after that, we just test it. So we want to test two cases. We want to test a case when we propagate forwards. So we start from the source, we set some value in the source, and then we process forwards. So we put this 10 in this node here. Okay, then that puts this 10 here. Then when we say process forwards, this 10 goes onto input pin of the transform. It gets ingested, a function that we define is called, and some value here is calculated, and this value is sent to this input pin of destination, and destination will ingest this value. In the second case, we want to check if process backwards works correctly. So we need to use a different value so that we can see that it actually works, because if we use the same value, we won't be sure if it worked. And we process backwards. So we set that value in the source, but we process backwards from the target node, from the destination. So we set the value here in the source node, okay? And we start from here, from the destination, telling process backwards. And what that does, it will go to transform node, okay? And the transform node will go to source node, and then source node will put the value here on the output pin. That will be received by transform node by input pin. So the value will be copied. Then the transform node will execute the function over this value here. It will push the result here to its output pin. And then the destination node will receive the value into its input node and will ingest the new value. Okay. All right, let's try to compile this. G++ minus minus std C++ 20 NodeGraph minus O bin NodeGraph. Okay. Ta-da! Let's run this. Okay, so we see there is some result of processing of our node graph. So our input in the first case was the number 10. The function we used was x times 1.5, so 10 times 1.5 gives us 15. And the second case was 50 times 1.5 is 75. So first case we processed forwards the number 10 through transformation function. And the second one we process backwards through the transformation function. So the node graph is working. So this is our full node graph demo. It's very simple node graph with just 3 nodes. The pins only allow single connections, and the nodes have to be allocated on stack, or they can be allocated on the heap if you have them in some data structure. But they cannot be allocated in a dynamic fashion. You cannot be adding new nodes to the graph at any random stage, right? Because for that you would need some dynamic approach, some polymorphism. And we will talk about it in the next chapter. One thing you can see here is that I put this comment. We cannot have a pointer to a node and delete it, okay? And that cannot be done because the structure of the node is private. It's actually protected. But yeah, we cannot be deleting the node, whether using delete or in any other fashion. So node cannot be instantiated because the destructor is protected. We can only use derived types, transform node, source node, and target node. Okay? We can delete those types because those types are known to us. They know how to delete themselves. They have public destructors. Okay? We cannot use those as node. I cannot have a reference to a node and assign to its source node. I cannot do that. because source node, as you can see here is underscored, is inaccessible because the base class is not public. Okay, the base class is private, so you cannot do that. So why do I inherit privately? What's the benefit? So I have this virtual functions still in the node, okay, and those virtual functions cannot be accessed by the user code really, because user cannot cast the actual nodes into a node because they are privately inherited, right? So target node is a privately inherited, and source node is privately inherited, and transform node is privately inherited. However, those functions are virtual, they are implemented in those classes. So for example, process backwards is an override of process backwards in the base class, so it is publicly available, so you can actually call it, but you're calling statically this particular implementation, so you're never gonna call virtual implementation. The only case when the virtual implementation is called is from the pins. Input pin will call process backwards, and output pin will call process forwards. And this is possible because pins have access to node references. You can see that pin itself has a node reference. There is nothing preventing you to have a node reference. Having node reference is not prohibited. What is prohibited is to use any of those target node, source node, or transfer node as a node reference from the user perspective. However, the target node can use itself as a node. So yeah, you can say construct input pin from the reference to myself, to the base class of myself, right? And same with the source node, I can construct output pin with a reference to the base class part of myself. And the transform, right? So those pins, they will call virtual functions. The pin will call process backwards in case of input pin, or process forwards in case of output pin, in a virtual fashion. So this is a virtual call here, right? Because pin has to call in a virtual way. This pin here doesn't know the type of a node it is attached to, right? It doesn't know the type of a node. So it has to call virtual process backwards. This pin here doesn't know the type of a node it is attached to, so it has to call process forwards, right? So this is a virtual call. But when we create nodes in our code, the types are statically known. They're known at compile time. So I created this transform node, I created this source node and target node, and all those method calls, they are statically known at compile time. So they're not virtual calls at all. Okay, so there is some benefits of not making the structure virtual and from making it protected, as well as from private inheritance, right? So we can see that in this design, the destructor is protected, which prohibits user from deleting the node, and it doesn't require us to define it virtual destructor. So we still have polymorphism, but we don't need virtual destructor. That's one thing. Another thing is that we still have polymorphism, but it's private. It's a private polymorphism. User cannot access those objects as their base classes. It's prohibited. Only those classes can access their private base class, right? So that's the beauty of this static design. Now, what is this static design useful for? This can only be used for specific configuration of the nodes, specifically connected nodes. So you wouldn't be able really construct dynamically this graph. So yeah, so this is our static graph. Right, guys, it's time to implement this node graph in Rust. We're going to implement static node graph. So the same as we did for C++, meaning that all the nodes are located on the stack. They are known at compile time. Alright, so the first thing we need to do is to define a graph node. It's going to be a trait graph node. Okay, so a graph node is going to be a trait with process forward and process backward methods. Now, the next thing we need to define is graph node pin. So it's going to be a struct. Alright, so we have a graph node pin here. So Yeah, I've done a little bit of digging, and I found that in order to achieve my static graph node, I will have to use things like referential option, and then I have to use this din here because otherwise the graph node pin would need to know the graph node type, exact type, and that would be difficult to achieve because we would have some sort of recursive types. So how about we implement this graph node pin? Okay, so this is an implementation of graph node pin. We have a setup, connect, set data, and get data. So let's look at this for a moment. So our setup method is kind of tricky one, okay? So we have this kind of self-referencing type, okay? So we're gonna have a node, graph node of any type, will have members which are pins, okay? Let's look at the picture again. So the node, right, will have a member which is a pin, and there's a little problem because the pin needs to have a reference to the node, so this is like a self-referential type, right? In order to achieve this in Rust, I created this setup method which will take here the reference to self with a known lifetime at that time, okay? And at this stage, we already created the pin with default, okay? So we see here there is derived default for this pin, so that we can actually create the pin without specifying a node. And then after creation, we're gonna use this refcell feature and option to replace it with actual reference to a node, right? So refcell allows us to mutate the value in the refcell, whereas option allows us to have a default of none. So when we create the pin, it's going to be none. And then when we call setup, we replace that none with the actual node, which is actually dynamic. So that's a virtual table. Okay, so this is how we sort out the self-reference to the node from the pin that is in the node. The connect method is, so that's another one. So we have to connect two pins from this pin to this pin, and connect have to go like this, right? And then it has to be called on this pin as well, and it has to go like this because it has to be bidirectional connection. So I decided to implement it so that in the pin itself, if graph node pin, I'll give it just one direction of connection, and then I'll have, because here you don't have inheritance in Rust, right? So you do composition. So I will have input pin and output pin, and I will contain this graph node pin in the input pin and output pin, and I'll sort out the bidirectional connection there. So let's define an input pin. So the input pin will contain the graph node pin inside. Let's implement input pin. All right, so this is the implementation of graph node input pin. We have very similar implementation to what we have in C++. The connect method, first so this is the input pin. First it connects this pin to this output pin here, and then it connects this output pin to this pin, okay? The received data is also very similar to what we have in C++. So for this input pin, it will retrieve data from this output pin, okay? As we can see here, we call set data on the current pin using the get data on the input pin. And propagate backwards is also very similar to our C++ code, where we take the connected pin, the node that's attached to it, and we call process backwards. So if this is our input pin, we go to connected pin, and we go to the node that's attached to it, and we tell the node to process backwards. The node will, go to its inputs, tell the inputs to receive the data, and it will do some processing, right? Alright, so that's the input pin. Let's define the output pin. So this is our output pin. It's very much the same as the input pin. So the only reason we have a different type is to distinguish between the implementations. We'll have a different implementation for the output pin than we have for the input pin. Input pin has receive data and propagate backwards, and the input pin connects to the output pin. For the output pin, we connect into input pin. We have send data and we have propagate forwards. So the output pin has the methods reversed as compared to input pin. So this is the output pin. Connect will connect into this input pin, and then it will tell this input pin to connect to this output pin. Send data will go from this output pin and set the data into this input pin, and propagate forwards will take this output pin, will look for the connected input pin and the node that's attached to it, and we tell the node to process forwards. In this case, it won't do much. However, this output pin will find this connected pin, will tell the attached node, which is transfer node, to do processing of this data here, and transfer node will put the output onto this output pin and will then tell it to propagate forwards in the same fashion. So put the data onto the connected input pin and tell the next node that's connected to that input pin to process forwards. Alright, so we have defined input pin and output pin. Let's define some nodes. Let's start with the source node. So this is our source graph node. It has an output pin. This is our source graph node, and this is the output pin. The implementation of source graph node has setup, which will attach itself, the source graph node, into the pin that it owns. So the reference is set from this pin to the source node. And we also provide the helper function to load value. The load value is a function that user calls on the source node in order to set the value on the output pin of the source node. Next, we need to implement graph node trait. We can see that for the source graph node, we implement process forwards by sending data to our output pin and telling output pin to propagate forwards. So we implement graph node trait for this source graph node by sending the data from this pin into connected pin and then propagating forwards that will cause the next node in the chain to process the input. Let's implement target graph node. Target graph node will have an input pin, which will be graph node input pin. It will also implement setup, which will set the reference, and it also implements getValue helper function, which will allow us to get the value from the input pin. So the target node will have an input pin, and the setup method will set the reference to the target node. And we have a helper method to get the value, which will get the value from this input pin. Next, we need to define graph node trait for the target node. We can see that for the target graph node, we only implement process backwards. So on the input pin, we call propagate backwards, and then we call receive data. So on the input pin, we call propagate backwards, right? And that will continue. And then we call receive data. This will receive the data. Some function will be called. Some value will be set. And we receive data. Okay, so we have source graph node and a target graph node. Now we can define transform graph node. This is our transform graph node. It has an input pin, an output pin, and a transformation function, which is a function object taking input type and producing output type. Okay, so the function object is in this transform node. The input type is a type of the data on the input pin, and the output type is a type of the data on the output pin. So the input type is X, the output type is Y, and the function is X into Y. We define the constructor and we define setup. Again, for setup we need to set self-reference to the transform node. So we need to set the self-reference for the input pin, and we need to set the self-reference for the output pin. We also need to implement graph node trait for the transform graph node. The implementation is very much the same as the one we have seen for C++. So we implement process backwards and process forwards. Process backwards first propagates backwards on the input pin, then it receives data from the input team, and then it calls the function on the data in the input pin, and the result it sets as data of the output pin. Let's see on the picture. So for this transform node, process backwards will first propagate backwards on the input pin to the output pin of the source node. It will call process backwards on the source node. The source node has a value set here on this output pin. The next thing, we will be receiving the data from this output pin onto this input pin. And the next thing, we will call the transformation function. Okay? And eventually, once we have a result, we set it here on the output pin. Process forwards works in the opposite way. So we first get the data from the input pin, pass it into a function, and set the result of the function on our output pin. Then we call send data to send the data from our output pin to connected pin. And then we say propagate forwards to continue with the processing. So process forwards, we first get the value from this input pin, we evaluate our function, we set the result of our output pin, and we call send data that will copy this value from our output pin to the input pin of the next node, and then we call propagate forwards, which will tell the next node to process forwards. Alright, it sounds like it's a graph that will work. Okay, so now we need a test case. So this is our test case. We're building the graph like on the picture. So we have one source node, one target node, one transform node. So for source node and target node, we can call default to just create default source node and target node. For transform node, we call new to pass a function foo, which we define here as a square. So it takes an int, it returns an int, and it returns a square of x. Okay? We call setup on each of the nodes to make sure that their pins are referencing the parent node. Next, I'm connecting the pins, the input and the output of the transform node, to output of the source and the input of the target node. And here we're doing the test. So I'm loading a value of 10 into source node, and I'm calling process forwards on the source node. I'm getting the value from the target node to then check if the graph has executed correctly. And in this second case here, I'm loading a different value to make sure that the graph will calculate new value. And I'm processing backwards from the target node, so in the opposite direction. I'm getting the value from the target node so that I can check if it was evaluated correctly. Let's see if this runs. Oh right, it compiled. Look at this. 100 and 400. Makes sense, right? So if we put the value 10 in the graph and we square it, we got 100. If we put 20, we get 400. So it looks like the graph is working. So yeah, so this is our, static node graph. It's static because the nodes are created on the stack. Their types are known at compile time. And all the connections between pins use references with lifetime tracking. Alright, so we have learned how to implement static node graph in C++ and Rust. Thank you for watching, and see you in the next videos. I'll be talking about the dynamic node graph in C++ and Rust.